All right, well, hello everyone. My name is Carl Dukatz. I lead the quantum computing program here at Accenture. And I'm here to talk about business experiments, quantum business experiments that we've been running over the course of the last 5 years. And really I'm going to talk about the most recent ones that we've done and some interesting stories behind them. So here's kind of the agenda for the talk. The recent experiments will cover some housing pricing, vehicle routing, autonomous driving, controlled agriculture, and railway freight planning. And then have some time for questions at the end as well. Just to orient you on how we work and what we do here with our business experiments approach, it's very common to, I think, what you've seen some of the other companies do as far as help analyze and discover and explore new use cases. We have been doing this for some time, so we have a very large database of existing use cases, so great places to start, but we also like to do design processes in order to really identify and isolate the things that we think are most important and will be most valuable to move forward with in quantum computing for businesses. And this also involves understanding which data will be brought to the problem, or which data will be brought forward to be used in an actual analysis. Next phase we call proof of concept. This is really about algorithm analysis and identification and mapping data to algorithms, building test cases. A lot of this is done in Jupyter notebooks in order to execute and run using real data, a quantum method or proof of concept. And once we've evaluated that a runtime can actually happen, then we will make a selection on whether or not to move on to the next phase or not. Also during this time, we like to have whoever we're working with, if they're unfamiliar with quantum, shadow so they can gain some experience with algorithm design, method design, and formulations. And then lastly is a prototype. And so this is something that I don't think a lot of other groups offer, but we like to create and architect an actual application that uses modern technologies that is scalable with the solution that we've designed. Because what we're doing is preparing and planning for the future with these applications. It's all about business readiness, business experiment, and then scalability and adaptability as new hardware comes out, as new methods are found, and really being prepared. So we institute all of those architectural designs that you would expect. So I want to talk through a few recent examples. The first one I like to call scoping up. So this is, we started this one with this idea that we're going to start somewhere, do a formulation, do an analysis, and then we found ourselves in a completely different place at the end, and it expanded our thinking about this particular topic. So as you guys may know, or anyone who has a more mature quantum program, you're monitoring new developments in toolkits, you're monitoring formulations, you're looking at publications that are coming out. We're constantly thinking about how we put them to use. And so earlier today, you heard about QCware's quantum, oh my gosh. You heard about their, no, not the Force platform. You talked about a specific use case, the KNN, so the clustering algorithm. And he mentioned it in a form of where they use it for machine learning to do image analysis. And so we decided that we could take and build on top of this work. It was a k-nearest neighbor method, and apply it to a housing market use case and identify what options there were available in order to do housing pricing estimation. And really the thing that was interesting about this is we started in one place where we thought about, ourselves and what we would like to see if we could get housing estimation better, how that would benefit us as individuals looking for a house or shaping and understanding the market ourselves. And then we thought about the business aspects of this, how it would be useful for real estate agents, for buyers and sellers, and then for banking and for insurance. And then we also started talking with some of our colleagues in the federal side, and they said, look, this is really actually very important for stimulus and assistance programs, having the right pricing and getting the accurate information about this correct so that you can help the public and impact society in a greater way. And so we really scope this idea up from just where could we apply this as a concept, but then also bring it all the way up to being useful and beneficial for society. And so I thought this was a really good example. And so I'm going to show quickly here what this estimator does. It's very simple, but you should get an idea. This is kind of weird because I'm not sharing my screen. So this is our platform where we host our demos for quantum computing, and this one's in the financial services sample. We'll launch our housing estimator. And so we use data from a public data source from the Ames data set. What I really wanted to do with this demo is actually just toss a URL up and have you guys all go in and type in your address and give you an estimate. But we had a limited data set and limited time to throw this together. And so in here, you can select all the different neighborhoods, different types of home styles, and the construction, the room size. I'm just using the defaults here. You can adjust the number of bathrooms or fireplaces, all the typical things that you would expect in an estimator for housing. And then using this clustering method through QC-ware, which is actually going down and running on IBM's hardware, we'll get an estimate for the house that we put in, right? And so the value of building something like this and the aspects of how it can be used and thinking about that in the future and the power that quantum computing can bring behind this simple use case was a valuable exercise, I think, for all of us in the discovery process. So this is one example, and we'll keep going here. If I can find my mouse. So the next one, I call it, let's see for ourselves. So vehicle routing, right? I think it's kind of a fun use case in the sense that everyone you talk to about this problem is basically at odds. So you have hardware folks saying that machines aren't big enough yet. You have algorithms folks saying that there's no provable speed up. And then you have the actual practitioners and the folks that do optimization saying, well, this problem's actually already solved, so why are you even bothering? And so it's kind of an interesting place, but I see it as an opportunity, kind of as a benchmark, because we know it's not actually solved. We know it's an NP-hard problem, and it's really about finding the right fit and the right way to do optimization that is useful, that I think we're all looking for a way to discover. And so we've tried this several times in the past. In 2018, we did truck service, telecommunications service routing, where we had 3 trucks in 9 locations, and we used one of the first IBM computers that was available to do some optimization on that, and figure out the paths where these trucks could go to make deliveries. And we showed interesting reduction in fuel consumption, but the problem was so limited that you couldn't really take it anywhere. And then in 2020, we did this again with end-to-end supply chain, where we looked at smart speaker distribution, manufacturing distribution in China. I know the picture is the US. We also applied a few different data sets here. But a bunch of different locations, many more routes, many more constraints, using a plethora of different technologies. And so again, this year, we decided to actually, with a client, tackle this package delivery service type problem. And the twist was, rather than just solving the routes with deliveries to direct locations, here we had a multiple truck problem that was also then allowed to not just go to the depot, but also make additional stops, pick up additional packages, and then go to more locations. And so by converting this problem from just the classical linear route to a multi-dimensional problem, we found that it actually fit better and performed more efficiently on some of the quantum devices because we increased the dynamic nature of the problem. So I'll show that one real quick as well so people can get an idea for what it looks like. Definitely a increase from, where did we put this? In all right, so this just goes through a little intro. Yeah, it's a integer problem. Cool, cool. Okay, so here's a map. We have some different depot locations we can set, different pickup centers, number of trucks, number of deliveries. I'm just going to generate routes for this. And I should also mention that some people in the audience may be saying, wow, that's really fast to be getting results from a quantum computer. We do a tiered approach to processing for all of these demos. So first, there's a cache, right? That's a standard approach for any type of web system. Then secondarily, there are also a combination. It can be a classical solver. It can be a simulator that the system can access depending on the availability of the quantum devices. And then there's also multiple different quantum devices that we can route to on the back end. Obviously, like using QCware or one of the other frameworks, there's a lot of flexibility in how that processing actually happens. But you can see here, we got the results. We can look at the actual vehicle routes, understand the starts and stops when they did additional pickups. And then there's also information about, here. We can get a more detailed dashboard view with aggregate information and actually a cost. This is based on the driver as well as the miles traveled to get an estimate for how much you would potentially save by running this route or doing it. So another interesting example of us moving the ball forward slowly on routing, finding out new things and experimenting in different ways. All right. Next we have, I call it challenge accepted. So we heard a lot already about this BMW challenge where they put out 4 different opportunities for people to step up to the plate and take a swing. We took a swing at the autonomous driving sensor optimization problem. And we're actually really happy with our results. We hope we win. But the idea here is that you can increase safety and reduce cost for vehicle manufacturing if you're able to position sensors appropriately around the vehicle to maximize coverage. And we not only developed an algorithm in order to be able to, a series of algorithms in order to be able to optimize where the sensor locations are, but also create a workflow so that this can be repeatably done for multiple different vehicles or different vehicle types. You can kind of see along the bottom here, it starts with a single dimension sensor looking for obstacles. You take that single dimension and there's a whole bunch of different algorithms that you have to determine which way directionally the sensor should be faced. You typically have multiple sensors that need to overlap and in order to look for obstructions. And then finally, you have to do that in dimensions all the way around the vehicle in order to actually provide full coverage. And so here we have a little video. See if it started playing. That shows what this looks like. So we recruited Accenture, acquired a business called Macavision. They do the graphics for series such as Game of Thrones. They also do modeling for cars, for commercials, and for actually on the internet, if you're going and selecting customization for your automobile, they're rendering all of that stuff on the fly and delivering it to you in real time. So this is an example. The video shows what this looks like and then how the optimization method can be used. So you'll get, I think, some more on that later. Another example here, I call it growing up. So our quantum ecosystem continues to grow, and we see momentum across hardware, across investments, discoveries, education. Everything that we're looking at is going as far as we can tell, in the right direction. But in another sense, when I think about growing up, I think about stepping back, looking at the bigger picture, and looking at how quantum computing can, affect and change society and solve larger problems and larger societal problems. And so we have a program, we call it Tech for Good. And the first pass that we took at this was with a kidney exchange algorithm. And so the idea was that if we can optimize all of the features for donor-patient pairs, then we can get more people more organs, essentially, that they need to live. And so that was kind of our first foray into Tech for Good. And then we did another one where we looked at radiotherapy scheduling and the optimization that is involved there, not just with the scheduling, but also with the beamlet angles so that radiation is hitting the cancerous area and avoiding healthy tissue. And that was a really exciting project, but it's still, with all of these, too early to implement, just building frameworks, isolating the variables that go into the problem, and figuring out ways to apply quantum and solve them in the future. And so this next one was a really cool one where, and this is why we call it growing up, it was with vertical farms and understanding the optimizations that can take place in controlled agriculture environments so that you can increase crop yield and reduce waste as you're as you're operating a crop or as you're operating one of these farms. And so we worked with a company called Intelligent Growth Solutions on this one. And you kind of see an example output in the lower corner. There's much more that goes into this, but really what we were optimizing was if there is a opportunity to introduce a delay in the growth, can you create a better yield and control the production such that you match demand more effectively? And really the variable there was if you put the lights at 50%, it will reduce the growth of a plant. So you have to monitor growth, understand what those dynamics are, and then figure out a way for one of these environments. And it's kind of hard to see there in the purple, but like this is a vertical farm. These pink lines are going up, and you can see here some of the lights and the way that they do it. And so this was an interesting problem, and we think that in the future this could help again with some of the societal things that would be wonderful and useful. And so then finally, this one I call a long haul. And I think Alex is in the room somewhere right here. So about 2 years ago, Alex Luna approached a couple of us, 1QBit and Accenture, and said, hey, I have this really awesome idea about how to increase efficiency in railways. And we said, that's wonderful. Like, what do you need? And he said, well, I have this and this and this and this. And we said, well, there's not much we can do for you right now. But if you work on this and if you, take your passion, put it into a business and develop something useful, come back to us and we'd be happy to work with you and happy to collaborate with you on the topic. And so that's exactly what he did. He worked through the Creative Destruction Lab. He worked with 1QBit on some algorithm design and created a railway freight planning system that instead of the railways in their freight calculations having to rely on static scheduling and customers being forced into a demand model, he re-envisioned that process using dynamic scheduling and started in the quantum model and then moved into an inspired approach that can be useful today. And so we thought that this was very powerful, and so started collaborating with him. And I wanted to share, some of the example results from a short line railway that Alex had worked with that we took some time to visualize. And what you'll see is this planning algorithm, which has many, I didn't even include them all on here, many different facets of all of the operations of a railway. And you'll see it optimizing the scheduling, optimizing what goes on the train, where the train is departing from, where it's broken up, the the crew, and everything that goes into account. And you'll see slowly as the algorithm works out, this is over a week, the red lines and all the lines that are increasing cost, increasing loading time, and increasing emissions essentially from the railway network. And on the left, this Artemis solution, you'll see long periods of nothing happening. And that's because the trains actually finished early for that day because they were further optimized. And you saw the animations of how the trains are moving on the network. And so this was a powerful example that we're happy to be in collaboration with. And then finally, I have one more thing that I just wanted to share. And this one is, I have this play here. This is kind of like an ADSI video, but we've been working with several different quantum computing partners to create a VR experience so that you can go in, see these different quantum computers in VR, understand some of the inner workings of them, see the component pieces, and become more acquainted with the hardware if you can't make it out to visit one of their locations. And then in addition, what we've been doing is some of these examples that I've shown, building them into this VR environment so you can get more hands-on with some of the applications that we've built. So this one, for example, Q-Power, this is a energy grid optimization method. And there are several other ones in here, but hopefully we'll be able to make that available for you guys so you can explore and experience quantum computing in a little bit of a different way. So with that, I will pause for questions. Yeah. Healthcare. Yeah, so we have done a couple of, so the radiotherapy one that I talked about earlier is a big one. And then a lot of stuff more in the life sciences side, which is we've done work in protein folding analysis as well as drug discovery, so small molecule and molecular comparisons. Sure. Yeah, so for each of these applications, we do a benchmarking exercise that says, in most of them, it actually revolves a reduction in order to run on the quantum computer in the first place. So we know that it's not going to be operational at business scale. Yeah, so the question is, are we tracking the complexity of the problems and understanding when advantage is going to occur for those problems? And the answer is yes. Yeah. I'm not going to dive into it right now, but we can talk about specific use cases if you want. Yeah. Right. All right.